Previously we mentioned metals could have BCC structure or FCC structure, and now let's look at FCC and BCC here. So for a BCC, which is a body-centered cubic structure, we have an atom at the center of the cube. Let me draw the diagonal line of the body, the cubic. So that atom here is at the center of the body. And inside of this BCC crystal structure, and can you count how many atoms inside of a unit cell? So this, what I'm drawing here, it's a unit cell. Let's count how many atoms we have. Let's look at the atom at the center of the body. That is one atom. And at each corner, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 corners. At each corner, it appears there's an atom at each corner. However, if you can see this unit cell is inside of a lattice. So at the corner of this cube, that atom there is shared with other 1, 2, 3, 4, 5, 6, 7, 8. It's shared with 8 other cubes. So the atoms at a corner is only 1/8 of an atom, if that makes sense. So in this case, the total number of atoms inside of this BCC structure is 1 atom. That is the atom at the body center, plus 8 times 1/8. That's count for the atoms at 8 corners. Then turn out that we have in total 2 atoms inside of a BCC unit cell. And if we look at our APF, what's the APF gonna be? As we learned previously, APF equals the volume of all the atoms inside of a unit cell versus the total volume of the unit cell. And if we know the length of this unit cell, it's A. So the length is A for all the sides, since it's a cube. So the total volume of the unit cell is gonna be A cubic. Then if we know the length is A, how can we find out the volume of the atoms? And here we use a sphere model. So even I draw the atoms at each corner, but actually atoms are touched if you look at the overhead slides. And if let's cut this from the diagonal, body diagonal here. If we cut this unit cell from this plane, if you can see that, and let's draw the cross-section area. So at the center, we're gonna have a atom, and at the corner, we have another atom here. So actually the atoms are touched together with each other, and this is on both corners we have a quarter of a sphere, and at the center we have a full sphere. So now we know this length is A That's the length of the unit cell. And this length here, it's a diagonal. The length of diagonal, which is square root 2 times a. And now we know two lengths. Can we calculate what's the length of this line, the body diagonal? The reason we want to know what's the length here, because if we know the length, we're able to calculate what is the radius of each atom. How come? Because if you look at this, at both corners we have a quarter of a sphere, and the length there give us one radius of the atom, and at the center we have a full sphere, so the length there is 2r. Therefore, we know the diagonal, the length of the diagonal, it equals 4r's. Since here we have a triangle, we're able to build a relationship. It's 4r squared should equal a squared plus 2a squared. Now we can find the relationship between r and a. Since in most of the cases a is given or r is given, you need to, in order to find APF, if you only know r or a, you need to know the relationship between them in order to convert them, all of them in terms of r or a. Here I would just convert r to a. So let's write an expression. R equals 3a squared over 4 square root. So that's a relationship between r and a. But remember, keep that in mind. This relation, let me highlight this relationship here. This only valid for BCC structure. And for FCC, we're going to do the same analysis again to find the relationship between R and A. Okay, now since we have the expression for R, and to calculate APF, we need to know what's the volume of an atom, right? And the equation to calculate volume of a sphere is, let me pull it up. It's 4 over 3 times pi times r to the cubic. So let me write out. So in total we have 2 atoms. Oops. We have 2 atoms times the volume of each atom is 4 over 3 pi r cubic. Now we know the expression of r in terms of a, and we can plug that in to find out the volume, the value for APF. It's let's see here. Yep, equals 0.68. Highlight this. Oops. Therefore, for BCC structure, our APF, it's 0.68. So it doesn't matter what is your length of the unit cell or the length of the radius, the value of the radius, the ratio gonna be a fixed number. So this is actually a very good packing efficiency. So this APF tells you how dense are atoms packed inside of a unit cell. Okay, I believe now you should understand how to calculate APF. Can you try to calculate what is APF for a simple cubic structure and for FCC structure?